Take a look at another example. Bell schedule. The student government finds that 30% of students in the survey want to change the bell schedule. However, so they took a survey and 30% wanted to change the bell schedule. However, 35% of the entire student body at the high school wants to change the bell schedule. Again, that's kind of the fantasy there. We don't, this is the thing that we're not going to really know in real life. Okay, but suppose we know that 35% of all students want to change the bell schedule. So identify the parameter in the statistic. So these are percentages or proportions. So if we wanted to go back and reference our little table here, proportions or percentages for the parameter, we're going to call it P. For the sample proportion, we're going to call it P hat. Okay. So the parameter equals the population proportion, which is P equals 0.35. That's the true percentage of all the students that want to change the bell schedule. Our statistic is the sample proportion, which was P hat equals 0.30. Does this mean the student government made a mistake giving the survey or were dishonest? So just because this is 30% and this is 35%, does that mean they lied or that they cheated or that they were doing anything shady? Of course not. No. Sample values, sample to sample values will change, right? From sample to sample, our values are going to change. If the true parameter is 0.35, one survey might give 32%, another one might give 41%, another might give 36%. In fact, isn't it pretty unlikely that we're going to get a survey that gives us exactly the same thing as the population parameter? And of course the answer is yes. And when we start talking about continuous distributions, we kind of know the answer to that already. It's like it's very, very unlikely that the sample proportion will be exactly the same as the population proportion. Okay, so this idea is, so why might the parameter and statistic be different? Sample to sample variability. Okay, this is actually called sampling error. And this is the term. I try to avoid using it too much in stats because when I say sampling error, it makes people think that there was a mistake in sampling. But that's the word. It's called sampling error. It's the error in our sample to parameter. Okay, so we're going to call it sampling variability to maybe kind of avoid that word error. But we can put our big kids stuff on and call it what it is, right? So sampling variability is a term that refers to the fact that statistical measures taken from good random samples will yield different statistics from sample to sample. Okay? Sampling variability, sampling error, sample to sample variation, all kind of mean the same thing. Bias, so here's our definition of bias. Let's put a couple stars by this. Put 3 stars by this one, and up here at sampling variability we'll put 2 stars on that one. Okay. Bias occurs when a procedure generates a sample, usually from a bad sampling technique, that yields statistical measures that are consistently an underestimate or consistently an overestimate of the parameter of interest. Bias can best be displayed with a graphic. So suppose P is our true population proportion, so it's this value right here. And suppose we sample in some way, and we get sample proportions that are consistently an overestimate. This is going to be bias. This is what a bias technique would look like. Okay? An unbiased technique, if this is our true P, we're still not going to be perfect. We're going to get values that are above and values that are below. But they're going to balance. On average, they're going to balance each other out so that they are centered. So the real definition of unbiased is if the mean of our statistic equals the parameter of interest. If the mean of our statistic equals the parameter, then we have an unbiased method, if you will. Okay? But if the mean of our statistic is different, if the mean of our statistic is not the same as p, as our parameter, by the way, we're using p not as p is a proportion, but I'm using parameter as a more general term, then we have a bias technique. Okay? So please, 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 when you use bias in this class, please refer to it like this and only like this. Okay? Don't say, well, that's a bias, you know, oh, that person's being biased, or this study is biased because, well, use it in this context. If you're going to use bias, then tell me why your sample measures are likely to be an overestimate or an underestimate of the true value. And if you're using bias in a different context, I would ask that you use a different word. Okay? What can cause bias in a survey? Bad sampling. For example, maybe I ask a question about politics and I kind of say, you know, do you believe in a woman's right to choose? Or do you believe that abortion should be legalized or made legal or illegal, or however you want to word it? If I ask a bunch of people in my friends group and I'm a conservative type of person, then yeah, you might get a much higher estimate than everybody, or if your friends group is very liberal. Or if you ask a question about gender equality and you ask a bunch of guys instead of girls or something like that. So if you just pick a bad sample can lead to this type of thing. Okay? There are other ways to do it though. There are other ways to get it. You could I don't know how far into this I want to get. We could you could ask leading questions. In fact, the minute I said it, I was kind of thinking about it. Do you believe in a woman's right to choose? You know, do you believe in a woman's right to choose? You might get certain responses to that question. And then another way I could say it, do you believe in, do you think abortion should be made legal? You know, and apologies, you guys, I don't want you to take this the wrong way, but do you believe that it's okay to kill babies? You know, I know it sounds horrible, but you see, like the same three questions. Like, do you believe it? Do you believe that it's okay to kill a baby before it's born, or something kind of like that? Like just a harsh way of saying it. Versus, do you believe in abortion? Versus, do you believe in a woman's right to choose? You know, a woman's right to choose. Who am I to say I take away a woman's right to choose? You know, if you ask this question, you could argue that all three of these questions are asking the same thing. You're asking about abortion, but the way you're wording it could elicit very different responses. So which one's the right way to say it? Well, I don't know. That's a good question. And there's just other ways as well. You know, the cop asking you, were you speeding, or something like that, or the principal asking you, or your teacher asking you, did you copy your homework? Peer pressure, social pressures. There's a lot of reasons why people may give responses that are different than their actual response, or different than the truth, or just change their responses for whatever subtle reason that's possible. So bias is a big issue. Okay, is it possible to prevent bias? Well, kind of. Good sampling can eliminate bias due to sampling, but and good questions can eliminate the leading question problem, and anonymity, doing an anonymous, oh my gosh, I don't know how to spell anonymous, whatever. Anonymous survey can perhaps alleviate social pressures, but maybe. I mean, if you took a survey at the school and it said it was anonymous and they asked you about, like perhaps like drinking or sexual behavior, your sexual behaviors or things that are personal to you, is it really anonymous? Are you going to feel comfortable sharing truthful responses? So statisticians spend much of their time trying to determine these types of things, or to try to prevent these types of things, but I'm not so sure they're going to, how easy it is to actually eliminate them. Right. When we had our students simply pick 5 words from the Federalist Papers and calculate the average word length, did that study have bias? How do you know? Let's go back to that picture. And by the way, let's just take a quick glance at this picture here. You know what to look for bias? If your responses, if your statistics, if your sample statistics are not centered about the true value, you have bias technique. And if your statistics are centered, then you have an unbiased technique. So if we go back and look at our surveys, the true value of the mean was 4.9. So as you can see, whenever you guys picked your own words, just whatever words you wanted, we definitely had a bias sampling technique. But when we use computer generation for randomness, now it looks like those values were nice and symmetric about the true value, so that's an unbiased sampling technique. And the nice thing about this was there was no other types of bias that we had to worry about. I didn't have to worry about whether the word I was going to be embarrassed that they were only 1 letter long and lie about how long they were. You know what I mean? Or observations like, oh my gosh, I'm so long, I'm so big. I wish I wasn't so big, so I'm going to lie about how big I am. Something like that, right? We didn't have to worry about some of these other forms of bias. So we had a perfect sampling technique. Okay. When we had students simply pick 5 words from the Federalist Papers, did that study have bias? Yes. How do we know? The mean of our X bars, the mean of our sample means, was not equal to 4.9, the true mean, the true parameter. When we use the random, did we have bias? No. Did that study have bias? No. The mean of our sample means, now it probably wasn't exactly 4.9, but was very close to 4.9. Okay. And if you're just to give you a little peek into the future, the mean of my X bars will be exactly equal to the mean of my X's if you take every possible sample of size 5. So 1, 2, 3, 4, 5, take that sample. 1, 2, 3, 4, and 6. If you take every possible sample of size 5, by the way, there's going to be a whole bunch of them. There's going to be 130, choose 5 samples of size 5. But if you generate all 100,000 of those samples and record the word length, the average word length, and take the mean of all 100,000 of those samples, the mean of X bar is not going to be approximately equal to the mean of X. The mean of our sample means is going to be exactly equal to 4.783, whatever that population mean was. The mean of every possible sample will be exactly the same as that. Okay, and that tells us that X bar is an unbiased estimator for mu. The sample mean is an unbiased estimator for mu. And now we're starting to get close to be able to talk about why we divide by n minus 1 on this one compared to dividing by n on this one for standard deviation. Because if you divide by n minus 1, then the sample standard deviation will be an unbiased estimator of that one. Okay, so we're getting close. We'll talk about it hopefully here in a little bit. All right, I'm going to stop here and do the next video.